All right, good morning. So here's going to be a quick beginning basic intro on magnetism. And there's not too many problems to work through in this one. It's just kind of understanding just the basics on what magnets are and kind of what they do. So it's very similar to electrostatics. But in general, I'm going to go through this, and it's going to be pretty quickly because I think I've written most of everything on the paper itself, so I won't have to add too much to it. So what are metals? Overall, or not metals, what are magnets? Magnets are certain metals, generally metals, which have two distinct ends. So one will be a north side and one will be a south side. And just it's kind of like positive and negative. So you got a positive side and a negative side, positive side and a negative side, positive side and a negative side. And just like electrostatics, you can draw these lines of force, and you can see the arrows. So what those arrows mean that is if you put a tiny test charge, just like electrostatics, that was north, not positive anymore, but north, little north test charge, anywhere on those lines, that's the direction that it would go. Okay, so if you put it right there, it would go away from the north and towards the south in kind of a loop like that. If you put it over here, it would go straight away from the north and would end up doing a big loop like that to the south. Okay, and you can see different fields of line on different things. So if you have one like this, the classic U-shaped magnet, you go from north straight to south, essentially there. If it's somewhere down here, it's kind of going to go away from the north and then start going towards the south. And if you're on the outside, away from the north, and then it'll eventually come back to the south. So those are lines of force, just like electrostatics, but in this case, your positive is called your north and your negative is called your south. All right, we have different types of magnets. We have permanent magnets, which are magnets that are kind of always magnetized, or at least for a very long time. They might eventually run out. We have an electromagnet, which are very important, but they're magnets that are really only magnets if there's a current running through them. So if you connect them to electricity, then they become magnets. And then the last one is Ferro Magnet, which is a magnet that has strong magnetic properties. And really they're only elements such as nickel, iron, cobalt, neodymium, and gadolinium. So I would look up those if you're curious to see what they look like and how strong they get. At school there's a neodymium one, which is really strong. It's almost too hard to pull apart yourself. And then last of all, there I have this one called Magnetite, which is a natural magnet, or call it kind of the strongest natural magnet. It's because it has lots of iron. Iron is kind of the basic magnet element. Or it's called iodestone. So that's, you went looking for a natural magnet, that's the one you'd want to look for. Okay, so we have field lines, we have electromagnets. Again, that's only a magnet if current is running through it. So it says, to start off, two scientists, Oersted and Ampere, eventually found out that a current going through a wire would move a compass needle, which is weird because it's not a magnet, it's just a current. So this led them, or Ampere, to find that a current going through a cylindrical wire, or positive to negative, will create a magnetic field. And just kind of like gravity, it's stronger closer to the wire. Okay, but the direction of the field is kind of perpendicular, or it's kind of as shown here, or it's around the wire like that. So if you took a cross section of the wire, that's kind of what the field would look like. It would really be more lines closer in and less as you go far out. Here you'd see little sprinkles of magnet filings. That's how they show fields sometimes, and you can see it's darker here, which shows that there's more strength closer to the wire and less as you go out. Alright, so those are the magnet fields that can happen with current. So generally there's magnetic fields happening all in your houses, or whenever you're using electricity, there's going to be magnetic fields. Alright, now we move on to what is a solenoid. A solenoid is generally just one of these wires that we just saw, but they take it and they coil it into its own cylinder. So it's cylinder wire that's coiled into a cylinder shape, okay, with a certain amount of turns. This one has 9 turns, I think, or 8 turns. So here they have a battery. This is a battery, and your current, called conventional current, we always say goes from positive side to negative side. Generally, it's the movement of electrons that's really happening, but generally, historically, they always go from the positive side to the negative side. But we know that electrons are actually moving, but it's positive to negative. That's what conventional current means. So a current will go through this coil back there due to the battery, and because it's a current going through something, a magnetic field automatically happens. So we know that the magnetic field would go around the wire in a kind of cylinder. Where did my pencil go? In kind of a cylinder shape around this wire, wherever you saw the wire. Okay, so but as you get to here, you're going to have tons of circles going around these wires of magnetic fields. And because they're so closely associated in these spherical shapes, it ends up happening that they kind of overlap, and instead of going in their circles, they're kind of going to go in these field lines here, where they go straight in the middle of the coil and they go straight through, and then they go back around here and they'll end up coming back there. Okay, so this is what a solenoid is. It's just a current going through a wire, and it makes a kind of a magnet itself. So if you look here, here's a normal bar magnet, south, north, and you can see the field lines go like that. Okay, if you hollowed out this magnet though, you'd see that they go through the magnet and back out, just like this does. So if you look, it goes out and around through the magnet and keeps going. So really this coil makes a bar magnet. So a solenoid is just a current, but it makes a bar magnet. So that's an electromagnet. A solenoid is really an electromagnet. And then there's just another representation here. So you can see north side, south side of the magnet. Okay. So solenoids have lots of uses. You will see them in the future with generators, transformers, or motors. And then we go to Amperes Rule, and this just goes to tell you what side is north, what side is south when you're dealing with a solenoid. So one way you can figure it out is you bring a compass nearby and it'll tell you which direction, because the north side of the compass will point towards the south side of your solenoid. But here's a rule: if you don't have a compass, you point your right. This first point here is if you just have a single coil wire like that, and say the positive to the negative, say we're going in this way. You point your right hand thumb in the direction of the current, and curl your fingers on that hand like so. The magnetic field lines will mimic your curled fingers. Okay, so my curled fingers are kind of going into the page above like that. So the field line would look something like this, like going around that way, and of course there would be a bigger one further out. So it would be a cylinder kind of like that. So that's that first point. And it says, or with a solenoid, because solenoids have so many coils and they kind of overlap a little bit, it's a little more tricky. If you curl your right fingers with the current, so an example, this one here, the current is going down here and around, so I curl my fingers. I'd have to move my hand kind of like that, curl my fingers around the same way the current would go. And then point out your thumb. My thumb goes that way. Your thumb always points towards the north side. Okay, so you could try it with this one. That's one of the questions, so I won't do it right now. But you coil your fingers the same direction as the current, and your thumb points towards the north direction. All right. Now it says if you take a solenoid and place an iron core, or kind of like an iron rock, inside the cylinder. So if you place a iron rock inside there, it makes a way stronger magnet than the solenoid itself. And this is called an electromagnet. This was an electromagnet before, but when you put an iron core in it, it's a much stronger electromagnet. And then, so this leads me to the question, how are magnets different from electrostatics? Because really, I'm just thinking positives repel each other, negatives repel each other, but if you have opposites, they'll attract each other. So it's to me, it's the same thing. But curiously, when they look at it, a difference is the stationary particles in electrostatics will be attracted or repelled, as we know. But if it's a stationary particle, that means not moving in a magnetic field, it won't be affected by that field. So if I put a particle here and it wasn't moving, it wouldn't really be affected by that field line. But it says if they are already moving, that dot is already moving, it will be affected by that field line. And if it's moving more, it'll be affected more by that field line, which is very interesting. But we'll see that kind of in future lessons, so you don't really have to worry. It's just like a sneak peek. And the last one is a right-hand motor rule. Instead of the right-hand rule, it's the right-hand motor rule, because it kind of deals with motors. Because motors are really electromagnets. This will become prevalent when we look at motors. So what you do here is you have a wire right in the middle of kind of a north and a south side of a magnet. Okay, so you have north-south, so the field lines are going to go north to south, straight through. You place a wire through like this, and you're going to have a current. Here they're saying the current is going this way. So there. So the interesting thing, again, we're going to see this in future lessons, is the field lines go north to south, but because the current is not really a magnet itself, it forms a magnet, but it's not a magnet itself. It's not really affected. It's not going to go left, but it's going to be actually going upward. So there's a force from the magnet that forces this wire upwards because of a current. Again, we're going to see this later, but we can look at the rule at least anyway, so that your thumb points in the direction of the conventional current, which would be that way. With your open hand this time, so not curled hand, but open hand, point the fingers in the direction of the magnetic field, so it's going to be like that, towards that south side, and then your palm will tell you the direction the magnetic field applies a force on the positive current charges. And it's always perpendicular to the field. So here we have the conventional current, we have the fingers going to the south side, so that means this would be going downward, so it would push downward. One thing I noticed about this picture doesn't correlate with what I wrote. So this picture is not a very good representation of how you do it. So maybe never mind this picture and go by the rules here. Thumb points in the direction of the conventional current, and then open hand. So this one really should go down, kind of like what I was saying. All right, thank you.